Okay, now it's better? Perfect. And of course, the local organizing committee and Mohammed in first place for the very nice organization. So far, we have really enjoyed, and I'm sure that we will enjoy even more in the rest of the week. So really thank for this. Okay, today I will try to tell you something about Biconservative submanifolds, and well, the idea we can talk at the idea in the following way. So suppose you start with the space of smooth maps between Riemann manifold. Then this is a very general fact. You can consider geometric variation of problems, and for me, a geometric variation problem means that you consider a functional, but a functional that somehow reflects the geometry of the map. Think, for example, when you consider for an immersion, a functional that gives you the area of the immersion. And I just recall, for me, critical point is just a particular map such that the variation of this function with respect to any smooth variation of the map is zero. And once you have a geometric variation problem, you can consider this sort of Hilbert's principle. And the idea is of Hilbert, and can be traced back to his original work, Die Grundlagen der Physik. And what he says is that once you have your variational problem, you can define a special tensor, which is called the stress energy tensor. And this one is a two-covariant tensor, which is conservative at critical points. And the meaning of this is that the divergence of the tensor must be zero when computed at a critical point of your geometric variation problem. So the point is, what sort of geometric variation problem we want to consider? And the first one, very well known, is that of harmonic maps. And in this setting, the functional that I consider is the so-called energy. This one is the Dirichlet integral, or if you want, is the integral of the square of the norm of the differential of the map. And so your map, in this sort of thinking of variational problem, geometric variational problem, is a critical point of the energy, and is a solution of the corresponding Euro-Lagrange equation. The Euro-Lagrange equation, you can see here, is given by the first part is this minus d star d phi. This is the differential of the map. The differential of the map, you have to think of it as a section in the pullback bundle, so as one form with value in the pullback bundle, and then you can define the codifferential. But I would prefer to think of this tension field as the trace of the second fundamental form of the map. So the second fundamental form of the map is d star that I've equated with the nabla d phi. And if you want to have an idea of this equation, you can look at it in local coordinates. And now you realize that you have one first term, which is the Laplacian of the component of the map, phi gamma, and then you have one term which is not linear. In fact, this one is an elliptic semilinear system of PDE. But I will not use the analytic expression. And then the original motivation of Hill-Sampson, that in their celebrated paper they've studied harmonic mapping between Riemann manifold, was really to investigate the existence of harmonic map in a given homotopy class. This was really some sort of trying to generalize Morse theory in infinite dimensional manifold. And as I believe many of you knows, there is the celebrated theorem of Hill-Sampson was that if you assume that your codomain N as sectional curvature non-positive, then every homotopy class has this special map which is an harmonic map. And moreover, the map is actually an absolute minimum of the energy. Okay, so how can we try then to how can we try now to construct the stress energy tensor for the energy? So I want now to try to follow what I've told you in the first slide, about the Hilbert's principle and try to see what happened when we consider as a variational problem the energy. And this was done in 1982 by Baird and Hirsch, and they actually discovered that the stress energy tensor is the one that you can see in the middle of the slide, is this one. And of course, if you compute the divergence of this S, you just get this condition. This one is minus the tension field in a product with d5 of x. And so, when your map is harmonic, and harmonic means that the tension field is 0, you see that the divergence of S is 0. So, if you want, this is really a stress energy tensor in the sense of Hilbert. The divergence of S is 0 when your map is harmonic. One question could be, how can you guess S? Because, of course, also in the paper of Baird and Hirsch, you have the expression of the stress energy tensor, but in general, there is a variational way of describing this tensor. And in fact, there is. And this is, to do this, you just have to change your point of view. When we consider the critical point with respect to variation, we think to fix the functional, and we're looking for variation of the energy with respect to variation on the map. But what you can do, you can fix the map, and you can consider a new functional, f, which is defined on the set, now let me call just a set of smooth Riemannian matrix on your domain, and you say when you compute f on a matrix, you just compute the energy of the fixed map with respect to the matrix on the domain G. And if you do this, this was a nice result of Aristide Sannini in 1983. And the result is that if you consider this new variational problem and you compute the first variation of the energy, but with respect to variation of the metric instead of variation of the map, what you get this formula. And from here, you can see that here you have the stress energy tensor. So in other words, the stress energy tensor is the Euro-Lagrange equation of your problem, your variational problem, but with respect to variation of the metric instead of variation of the map. So this might be, in general, a way to guess the expression of S. If you have your geometric variational problem, you want to understand who is S, well, you just consider this new variational problem, you compute the Euro-Lagrange equation, and the Euro-Lagrange equation will give you the stress energy tensor. As I've written the title, my interest is in submanifold, or more general in isometric immersions. And suppose then that your map is an isometric immersion. So in this case, the tension field, as I told you, was the trace of the second fundamental form of the map. But in the case you have an immersion, the second fundamental form of the map is just the second fundamental form of the immersion. And if you trace it, you just get m, the dimension of m, times the mean curvature vector field. So from here, what you deduce the following fact, that if you restrict yourself to isometric immersion, then the harmonic ones are exactly the minimal ones. So in other words, you get a different way of thinking to minimal immersion. And then, if you start with the minimal immersion, which is from the line below, before harmonic, then the divergence of the corresponding stress energy tensor is 0. And so, in general, now, you could ask the following question. But, okay, if I have a minimal immersion, it is an harmonic isometric immersion. But if I start with an immersion such that the divergence of S is 0, has any meaning to study this new class of isometric immersion? Because the other inclusion here, okay, it's not clear if also the other way around is true in general. The problem is that for the image, this question has no meaning. In fact, let's compute the divergence of S. The formula of Baird is was that it was equal to minus the inner product between the tension field and d phi applied to X, which is a tangent vector. But this one, tau, is m times the mean curvature vector. And the mean curvature vector is always normal to the image of your isometric measure. Then is always normal to a tangent vector to the isometric measure. Then this one is always 0. And this means that this condition is true for all isometric immersion. So of course we can consider this condition, but we are just saying that is any isometric immersion. So in fact this probably has no meaning. So when you arrive at this point, you are tempted to say, okay, I just throw everything away because there is nothing I can do with this. But in fact not, because it says Samson, just 1 year after the celebrated paper in 1964, they have introduced a sort of higher order energy functional. They were already trying to give a notion that naturally generalized that of harmonic maps. And the construction follows like this. You consider a new functional that you call the R energy, and this one is given, this one is given by the formula. And what you have to do, you have to take d star plus d, and you have to apply this to 5 R times. This is the meaning. And then you compute the norm, the square of the norm, you integrate, and this is your new functional. When R is equal 1, you end up with the energy that I have already defined. But when R is equal 2, well, you get a new functional, and you see, if you do the computation, for R equal 2, you arrive to this star. Now, you just have to remember, in my first slide, minus d star d phi was the tension field. So really, this one is the norm of the tension field. So the function you get is this one, which is now called the bienergy, and we just put it 2. If we think a little bit, what is really this functional? So if you have an harmonic map, the tension field is 0. So this function is 0. In other words, an harmonic map is an absolute minimum of the bienergy. But if you have a map which is not harmonic, so the tension field is not 0, then what are you computing with this is really your kind of computing an average of the norm of the tension field along your manifold M. So in a way, when you look for maps that minimize this functional, you are looking in the class of maps which are not harmonic, the best one, those which have the average of the tension field, or the norm of the tension field, the minimum possible. So this is the idea of studying critical points of this new functional. And nowadays, this is a theory well developed, and everything started in 1986 with the work of Zhang. The original work was in Chinese, and for all the people that at the end of the 90s started this subject, they had to deal with this Chinese paper, which was dense and full of a lot of notions. But fortunately, this happened in a meeting in 2007, I think in Lecce. Giovanni will remember. Urakawa decided to translate the paper in English because he could understand the Chinese. And this was a big favor for many of us. Anyway, in the paper of Zhang, he computed the Euro-Lagrange equation associated to the bienergy, and this is the guy you have to deal with. Well, this one is a difficult equation. This is the fourth order semi-linear elliptic system of PDE, and in general it is very difficult to find a solution, to understand, particularly when the solution is not harmonic. Because if your map is harmonic, the tension field is 0, so automatically tau 2 is 0. So the big point in this theory is first to understand under what condition the converse true. So under what condition? Once you have a biharmonic map, must be necessary an harmonic one. And as a general result, but I don't want to talk about this, if M is compact and the sectional curvature of the codomain is non-positive, then any biharmonic map is harmonic. this is interesting because if you remember the two conditions, this geometric condition of the track, it is exactly the same condition of the celebrated theorem of Hill-Sampson. So in other words, the theorem of Hill-Sampson is telling you that you start from compact to a manifold with non-positive sectional curvature. In each multiple class, you have the harmonic representative. And here what he's saying is that you also have the harmonic representative, but actually it's the harmonic one. So in a way, it's trivial that you have the harmonic representative. So the big point is, well, but can we study harmonic map which are not actually harmonic, which have not identically zero tension field? And now let's go to the stress energy tensor, because also for the bienergy, one could try to compute using the Hilbert's principle the stress energy tensor that I would like to call the stress bienergy tensor. And well, this was computed already in this original paper of Junk. We have realized many years later. And it was computed, and you see, this is the expression. It's more complicated than the one I've shown you for the energy, but still, if you compute the divergence of this tensor, you get exactly this condition. So it's telling you that when your map is harmonic, that is, when your map has two tension fields 0, then this tensor is conservative. The divergence of this tensor is 0. And moreover, this is something we have noticed many years after this work. This is something we have done with Eric, which is here, and our colleague Cesar Onichuk, which is in Yash. And we have realized that the same property discovered by Aristide Hasanini for the energy works also for the bienergy. So if you want, if you consider the bienergy and you take variation of the bienergy with respect to the metric instead of variation with respect to the map, then you just get that the stress bienergy tensor is the Euler-Lagrange equation of the bienergy with respect to variation of the metric. So it is exactly the same result as Hasanini. And I believe that this result is general. I don't have a proof. I will also try to look for this in the paper of Hilbert, but I believe that every time you have a variational problem, every time you consider a stress energy tensor, I believe that every time this stress energy tensor is given by the Euler-Lagrange equation of the variational problem, but with respect to variation of the metric. I would like to have a proof for this. I don't. So some help might help from the audience. Okay. And back, now we go to harmonic isometric immersion. In this case, again, the tension field is m times the mean curvature vector, so your condition for an isometric immersion to be harmonic is that this guy is 0. So if you want, you can consider, this is one of the justification, you can consider harmonic isometric immersion as a larger family that includes the family of minimal immersion. So if you want, you can think that this is a fair or natural generalization of minimal immersion. And yes, I have 5 minutes. I would like to, because this is not the subject of my talk, but I would like to tell you just few things about harmonic isometric immersion. So few things about this red area. So first of all, this concept that I have described using a geometric variational problem started few years before with the work of Bang-Yen Chen, where he just said this. Suppose you have an isometric immersion of a manifold in Rn, then you can compute the mean curvature vector, and you can see the mean curvature vector as a map from M to Rn. And then you can compute just the Beltrami-Laplace operator of all the component function of the mean curvature vector, and you say that your map is harmonic in your immersion if delta of the mean, delta H is 0. And in this theory, the big game is to prove the following conjecture that was proposed in 1991 by Bang-Yen Chen, that actually for isometric immersion from a manifold in Rn, bar monicity, which is delta H equals 0, is equivalent to H equals 0. One way is obvious. If it's minimal, it's barmonic, and the big game is to prove from left to right. And of course, if you consider the notion I gave to you before of no, this is the point. If it is compact, it's trivial, of course. But the problem is that this conjecture is a local conjecture. So really, you have to prove this locally. It's really local in nature. And the conjecture, it is open. There are plenty of works, there are several cases when the conjecture is true, but the general case is not solved. And I would like just to spot to you the two lowest dimensional cases which are still open. So for hypersurface, up to n equal 5, it is known. So if you have an hypersurface up to n phi in R6, it is known that the conjecture is true. But in higher dimension, it is open. But more critical is that we don't even know if the conjecture is true for surface in R4. Here we are going codimension 2. So this is the first case. I believe this is really the first interesting case that should be solved. Surface in R4, trying to understand if barmonicity imply harmonicity, or if you want barmonic imply minimal. And if we move and we change the ambient space to a space with constant stationary curvature, a space 4 if you wish, then the condition becomes this one. Now, of course, to write this condition in the slide, I'm using the equation we have deduced from the variational problem. And in this case, when C is no positive, well, we have a generalized Chen conjecture, which is saying that probably also in this case, the game is to prove that you only have the minimal ones. But when Chi is positive, here you have examples. Here you have example, and we can restrict ourselves to the sphere when C is positive. And here are the two main examples. So the two main examples of barmonic submanifold hypersurface in the sphere, which are not minimal, of course, are those two. So the first example is you take your sphere and you just take a parallel hypersphere of a certain radius. And this one is a sort of product of sphere of generalized Clifford tori. And they both have constant mean curvature, not zero, and they are both examples of barmonic hypersurface in the sphere. And so the point is that, well, suppose this one is the set of constant mean curvature hypersurface in the sphere. And there are two examples. Then you can prove that the barmonic condition in this set reduce of asking that the norm square of the shape operator is equal to n. If you want to think of what is this norm of the shape operator, well, you have your hypersurface, you can consider the principal curvatures, K1, K2, Km, and this one is just the sum of the square of the principal curvature. And this one must be equal to n, the dimension of the domain. And there are two conjectures which are still open here, because one is to prove that in this set, one is to prove that all barmonic hypersurfaces actually are in this set, so that all barmonic hypersurfaces actually have constant mean curvature. And the second one is to prove that all barmonic hypersurfaces actually are only those two examples. So these are two conjectures that we have proposed in the 2007, and some work is done, but there are also those two conjectures are still open. And one thing that I would like to point to you is that proving conjecture 1 does not imply immediately conjecture 2. So I mean, if you prove that your hypersurface, when it's barmonic, is CMC, you cannot deduce that you only have those two examples. And this one really can be written as a general geometric problem. So this one has nothing to do now with barmonic isometric immersion. And the problem is the following. So you start with a constant mean curvature hypersurface in the sphere, not minimal, and you assume that the norm square of the shape operator is the dimension of the hypersurface. Then prove that there are only those two examples. And this one is a completely geometric problem, nothing to do with barmonic isometric immersion. But this problem has no solution. And well, here I just written some cases where this problem is true, but this is not important. What is important, what is important is that the minimal version is well known. So if you change CMC, there is CMC not minimal, not constant. If you change CMC with minimal, this is the famous theory of Chen, Carmo, Kobayashi, and Lawson. So in the minimal case, an hypersurface in the sphere such that the norm of the square of the shape operator is the, oh sorry, this one should be the n, is a mistake, is n, then we know that you are only in those two cases. But in general, if you move to this one here, there is nothing to do. And let me just tell you one thing. Here you see it is written that if you assume that this one is isoparametric, then it is true. They only have one of those two cases. Isoparametric means that all the, well, means something else, but just for short, means that all the principal curvatures are constant. And this is the point. Problem, another geometric problem. Suppose you have an hypersurface in the sphere. Sorry? No, well, in the way I've written it, yes, I'm assuming competent. Otherwise, you should prove that it's an open part of. Okay? But yes, in the way I've written, I'm assuming competent. I agree with this. And so the other geometric problem is, if you have an hypersurface in the sphere, it is CMC, and the square of the norm of the shape operator is constant. Can you prove that this is isoparametric? Can you prove that all the principal curvatures are constant? Of course, one way is true. If in an isoparametric hypersurface, all the principal curvatures are constant, so this one is constant, and this one, which is the sum of the square of the principal curvature, is constant. But this way, from left to right, is not known. This is an open problem. And I know some solution. I know that in some cases, this is we know a solution, but in general, we don't have a solution. If we could have that this problem has a solution, we could also prove part of our conjecture. But now, again, we need some help. Okay, so let me go to the main topic of my talk. So I've just used 5 minutes to tell you something about isometric, barmonic isometric measure. But now, let's go back to our stress energy tensor. So, if your map is minimal, if your isometric measure is harmonic, then it's barmonic automatically. And then, when it's barmonic, what we know is that the divergence of the bienergy stress energy, a tensor, which is called S2, is 0. And remember, when I told you about the energy, I've asked the question, can we study isometric immersion with divergence of S0? And the problem there was meaningless, because all isometric immersion have divergence of S0. But now you can. Now, if you can consider a new class of isometric immersion, the class of isometric immersion such that the divergence of S2 is 0. And why? Because the tau2, which is the two tension field, in general, it is not normal. So this one, it is a condition. And so here comes the definition. So this is the definition of the title. Biconservative immersion, if you like, immersed submanifold, is a map such that the divergence of the two stress energy tensor is 0. And so we have the following conclusion. We have the minimal submanifold, or minimal isometric immersions. We have the barmonic isometric immersion, which is the first generalization of minimal immersion. And then you have the Biconservative isometric immersion, which is a larger class. And I just want to point out that when you study isometric immersion such that the divergence of S2 is 0, look here, of course, really, you're asking that the tangent component of the two tension field is 0, because this one will be always tangent when you apply to a tangent vector of the submanifold. And just to point out that this notion of Biconservative immersion was actually considered already in a precise case of hypersurface in R4 by Hasanis and Vlachos, but the name was H-hypersurface. Many years later, we decided to call them Biconservative because the two-stress energy was conservative. Okay, now, as I've also written in the abstract, in January, the 9th of January of this year, Bang-Yen Chen wrote a paper, a sort of survey of what has happened in the last 10 years in this subject of Biconservative submanifold. But I don't really want to go through a survey today. I don't want to tell you a survey. I just want to tell you two things that I believe might justify the interest for Biconservative submanifolds or Biconservative isometric immersion. And to do this, I will restrict mainly to the case of surface in a Riemannian manifold. And, well, the first thing I would like to tell you is, well, let's talk about some classical topic. So, of differential. So, you have suppose you have a surface in a three-dimensional spacefold, and then you can define this function, which is called the of function. So, this one is a second fundamental fold, this one is a shape operator, and this one you just define. Well, to do this, you just have to start with isothermal coordinates of your surface. Then you have the classical operator dz bar, and then you can extend B by linearity. You can define B on dz, and then you have this function. This is a complex function. Well, here there is something written it looks like one of the things you find when they ask you to sign an insurance, no? And just saying that really you should give to deal with this function, you should give this function global meaning, and to give a global meaning, you should go through the associated quadratic differential. But in this talk, I will just stay with the of function, which is easier, and my work will be local, so we don't need to do this. And here all the details. Eta is just the global unit normal, and so on. Okay, so we have this function. And why this function is important? Because it was used by Hoff to prove his celebrated theorem. And the theorem was that a constant mean curvature immersed sphere in a three-dimensional space 4 is a round sphere. So if this constant mean curvature topologically is a sphere, it must be really isometric to the round sphere. And the proof goes as follows. First, you understand that this function phi, the of function, is holomorphic if and only if your surface is CMC, so as constant mean curvature. Then you understand that it is identically 0 at all umbilical points, so points where the principal curvature are equal. And then we have this topological fact that on a topological sphere, any holomorphic quadratic differential vanish everywhere. This is where you need this global fact that I've written in very small character. But I'm interested in the first thing. So, of course, once you know that you start with the CMC and you know that it's holomorphic. When it's holomorphic, you have that. Sorry, when phi is 0, you have the umbilical points, and then you use the rigidity theorem that we all know that a surface in a space 4 which is total umbilical must be actually a sphere. And then you use this fact that on a topological sphere this phi must be 0. This is just an outline of the proof. But I'm interested in the first point. So the first point is that your surface is CMC if and only if phi is holomorphic. And this is easy, because you just use quadratic equation and you write down this condition. So you write down that twice the derivative with respect to z bar of this function is lambda squared is this conformal factor of the isothermal coordinates of the derivative of the f is the mean curvature function with respect to z. So of course when f is constant, this is 0 and the other way around. Okay, so let's move to higher dimension. So let's consider a surface in a space 4 but of dimension greater than or equal 4. So in this case you cannot construct the of function because you don't have a unique normal. So to construct this one I have to use the uninormal vector field. But even in this case, when the condimension is greater than or equal to, you can of course consider h as a normal direction, the mean curvature. And then you can consider this new function that I call q. I mean, formally is the same, but just replace eta with h. And then, one fact which is well known from the 70s is that if you consider a surface in this space, then that is PMC. PMC means that is with parallel mean curvature. This condition of parallel mean curvature is stronger than having the norm of the mean curvature constant. If you want, if it is PMC, the norm of H is constant. If the norm of H is constant, it is not generally PMC. This happens only in codimension 1. But the result of Hoffman and Yao was that actually if you have a surface which is PMC, then Q is holomorphic. So, my question is, under what condition Q holomorphic imply that it's PMC or CMC? So, under what condition we have the other way around of this fact? And this question is actually interesting also for surface in a three-dimensional space form. So, let's do the computation. So, we take a surface. This is a three-dimensional space form, a space of constant sectional curvature C. We have the mean curvature vector, which is just given by the mean curvature function times the unit normal vector field. And if you do the computation, you compute the derivative with respect to z bar of q, you get this equation. Okay, we are back. And then you see that when Q is holomorphic, well, it's holomorphic if and only if the shape operator applied to the gradient of the mean curvature function is 0. And then you just have to remember that Gauss equation, the determinant of A is given by the Gaussian curvature of the surface here minus the curvature of the ambient space. But if you use this, you have, okay, when this one is different from 0, if you wish, when the Gaussian curvature is different from C, of course, this condition will imply that grad f is 0, and this means that your surface is CMC. But when the Gaussian curvature is equal to the curvature of the ambient space, for instance, when you have a surface in R3, which is flat, then if you just consider this cone when z is equal to minus x plus 1, this one is a surface which has Q holomorphic, but is not CMC. So this means that the other way around of this Yao-Hoffman proposition, it doesn't work in general. Okay, so this means that maybe there is something to do. And now I try to use the condition of biconservativeness to understand this converse. So consider the surface. Now, in any Riemannian manifold now, I don't want to restrict myself to constant sectional curvature. And we are trying to understand when this Q is holomorphic. We have a general fact. This fact, suppose you take any two covariant tensor, symmetric two covariant tensor, in a surface. This is a general fact that has nothing to do with the setting. Then any two of the following conditions imply the third. So the divergence of T is 0, the trace of T is constant, and T of dz is holomorphic. And now let's try to use this result for biconservative surfaces. So here we go. Here we have a Biconservative surfaces, and we compute the stress bienergy tensor. And the stress bienergy tensor for a surface in NN is given by this formula. So the formula that we had before simplifies a lot. But now, if you compute the trace, just do it, you get 4 times the norm of the mean curvature vector. And if you compute S2 applied to dz, do it, the first part is 0, and then you get 4 times this function q. And now we use the general fact, but we use the general fact when t is S2. So the first condition when t is S2 means the version is 2, so phi is Biconservative. The second one, t, but this one, this trace of t is just a multiple of the norm of the mean curvature, so means CMC. And the third one, S2 dz is just 4 times q, so means that this one holomorphic means that q is holomorphic. So in other words, since we have that those 3 conditions, 2 of them imply the third, I like to think the problem in this way. You have the set, the big set of Biconservative surfaces in any Riemannian manifold, and in this set you do have the equivalence. Sorry. So in this set you do have the equivalence. So in a way, this family of Biconservative surface is really the good family to see when there is an equivalence between Q holomorphic and the surface CMC. And using this, but just, using this, but just to show you, you can of course prove other result. How? Because you assume that your surface CMC Biconservative, you are in this family, then you know the Q holomorphic, you use the holomorphicity of Q, and you keep going to prove other result. This is the idea. Okay, in the last part, I have 6 minutes, not many, I hope, to be able to conclude. I would like to look at this special case of surface in a 3-dimensional space form. This is a very particular case. Well, in this case, the condition of Biconservativeness becomes just this line, A grad f plus f grad f equals 0. Believe it. And of course, if your surface is CMC, so grad f is 0, grad f is 0 is Biconservative. But now comes the point that just in this case, for surface in a 3-dimensional manifold, actually you can prove that barmonic implies CMC, which was one of the main conjecture I was telling you before, but actually this is true in this particular dimension. And this was proved by Bang-Yen Chen when chi is 0, and we proved later when chi was different from 0. And so, have a look. Barmonic implies CMC. CMC implies Biconservative. And minimal implies barmonic always. So, you have all these inclusions. So, we start with the minimal immersion, you have the barmonic isometric immersion, you have the CMC immersion, and then you have the large class of Biconservative immersion. So they are all proper inclusion in the case of surface in a 3-dimensional space form. And of course, where our interest is in this gray part. We would like to understand how are the Biconservative surface in 3-dimensional space form, which are not CMC. And here is it works like this. This is the condition. Then you realize that this E1 is just a principal direction. And the eigenvector, if you want, the corresponding principal curvature is lambda 1 equal minus f. You just put this on the other side, you divide. And then you just use that minus f is the mean curvature, and you do your algebra, and you realize that this condition satisfies. If you want, your Biconservative surface, which is not CMC, is a linear variant surface, where the linear condition between the principal curvature is this one. And using this, what we could prove is that actually you can realize, you can construct all the Biconservative surfaces in 3-dimensional space form which are not CMC as a rotational surface, And the profile curve really is a curve on a totally geodesic surface of the same constant curvature in the three-dimensional spaceform. For example, in R3, you see that Biconservative surface which are no CMC, they are given by rotation of a curve like this, which looks like a catenoid, but is not a catenoid. It's different. In fact, it's not even CMC. And the big question in 3 minutes is, okay, can we construct closed Biconservative surface in a three-dimensional spaceform? Of course, in R3, if the profile is of this type, when you rotate, you don't get anything which is closed. But in general, well, let's see. The first step is that this is something that we could prove with Alvaro Pampano. He came to Cagliari a few years ago, and he was an expert in this bending energy. A Biconservative surface is given by the rotation of a profile curve, but this profile curve actually is a critical point of this bending energy. And once you know that there is a critical point of this bending energy, the profile curve of your surface you are trying to study, you also have the Lagrange equation associated to this variational problem. So the problem of studying Biconservative surface is really related to the problem of studying critical points of this curve. And the first thing that you can observe is that this prime integral, there is a prime integral of this equation, and just a short analysis here. Now I will go quickly. You can rewrite this in this way, and you can do an analysis of this function q. What is important, this function q, which is the prime integral of the condition on the curvature of the curve you're studying, is that when c is positive, the graph is of this type. You have 2 points, and you have a segment where u is positive. U must be positive because it's the square root of k, which is positive. But when c is less than or equal to 0, the graph is something like this. So with another substitution, you call ux squared and yxs, the condition we have on the curvature of the profile curve really can be written this way. This is an algebraic curve in a plane, and you can use standard argument or square roots to understand that. To understand that when your curve is of this type, since to get the curve, you just get rid of the part which is below, you take the symmetric part, so you get a closed curve. But when you are, in this case, c less than or equal to 0, since because the graph is not this type, you have to stop here, you don't get a closed curve. So in a way, this one is a closed curve when c is positive. And then you just use some sort of general argument using Poincaré-Bendixson theorem to prove that actually this curve, which is given by the profile curve, is a periodic curve in this closed curve, and then you finish saying that your curvature actually is periodic. So means that if you start with a Biconservative surface, which is a rotational surface, in the case you go to this three-dimensional sphere, for example, then the curvature of your profile curve is periodic. But this does not mean that the curve is periodic. And to do this, you need to use a technique that was developed by Langley Singer in the 80s. So, the point is, you start with the curve. The profile curve lives in S2. And you can construct a vector field J and prove, and using the equation that the curvature has to satisfy for the surface to be Biconservative, you can prove that this vector is a Killing vector field along your profile curve. And then, the nice thing is that this one is a result of Langley and Singer. Once you know that J satisfies those two, you know that J is the restriction of the Killing vector field on the whole S3. So you have your curve, you have your J, but actually J is the restriction of the Killing vector field on S3. So you can parameterize your sphere, and what you really have, you have your curve gamma, which is the profile curve. And if you want a closed Biconservative surface, you need this curve to be closed, periodic. And you start following the curve, and what you can do, you can follow, and you can take the tangent vector, and you can look at the angle that your curve does with your Killing vector field J, And really, your curve, the curvature is periodic, but what you want, that when you follow your curve, eventually you come back. So you want that this angle that you form, if you compute the total angle, you want this one is a multiple 2 pi. But eventually you can go around the pole several times. So the idea along the thinking is that your curve with the periodic curvature is actually periodic itself if this condition is satisfied. That the total angle, when you compute in the period of the curve, is a multiple of 2 pi, where n, which is the denominator, tell you that the period of the curve is n times the period of the curvature, and n means how many times you go around the pole. And you can compute this function using the differential equation, and the big technical thing is to prove this lemma, that this function ed is always between pi and square root of pi, and it takes all the values in this interval. And why this one will solve you the problem, and sorry I'm finishing, because you take two numbers, m and n, such that the common greater divisor is 1, n is less than 2n, which is less to square root of n, you just divide, and you get this condition. But this one means that since ed takes all the values, and this number is between those two, you know that there is a d such that ed is this value. And when you have this ed such that ed is this value, you have a closed Biconservative surface. And so here is the theorem, and I show you just one example. So here you take m equal 3, n equal 2. So really, you follow 3 times the period of the curvature, and you go around the pole twice. And if you follow the curve here, you see that you go around the pole twice. The pole is here. And so this one is the profile curve in S2, and this one is stereographic projection of the corresponding surface in R3. And that's it. I hope the sentence is correct. Sorry for the 4 minutes delay.